Can you grab me gravel? Which one? Yes. Any audio noise here on YouTube? Check out. Check out. I plugged in charger. Noise? Noise? Little bit? No noise, isn't it? Little bit. Manageable, isn't it? Yeah. Now, we'll get into, so before getting into this differential equation part, I have to tell you something about the last session, okay? I mean, we have seen in case of what you call electron double slit experiment, okay? You had double slit, you had screen, isn't it? You have observed interference pattern, isn't it? You had slit 1, slit 2, isn't it? When you are not observing state of the particle, so that was in the superposition of two translational states. We call this one as translational state, okay? Not energy eigenstate. Psi 1, psi 2 I have written, okay? They are actually eigenstate of momentum. We shall see later. Kind of free particle, isn't it? Psi 1 plus psi 2. Is that okay? State of the particle that was in the superposition of two translational. Okay. So superposition of two translational state when unobserved, isn't it? When you do observation, so state of the particle, I mean, it will show off either this translation state or this translation state. Is that okay? So that was the observation. In the very similar manner, look at here. Here we had psi 1 of x comma t with energy E1, psi 2 of x comma t with energy E2. These are stationary states, okay? Psi 1 of x into e power minus I E1 t by h bar, okay? So similarly, psi 2 of x into e power minus I E2 t by h bar. These were stationary states or definite energy state, eigenstates of Hamiltonian, isn't it? Different name. Stationary state, eigenstate of Hamiltonian, or energy eigenstate, isn't it? Definite energy states. Now look at that. Now, so the most general solution or any other state, you can write that one as, look at here, linear combination of these state or linear combination of these state is also possible state. Cn into psi n of x comma t. So that is equal to, look at here, summation over n Cn into psi n of x into e power minus I En t by h bar. This is a kind of superposition state. Most general state. Is that okay? So that can be superposition of, we say superposition of energy eigenstate. Can I say like this? Superposition of different energy eigenstate. Speak out.
So this is not linear state.
This is linear combination only. C1, Psi1, C2, Psi2 like that.
Not like that.
No. Here you put 1 and 1 here. This is not translation state. Here we call this a translational state. Okay. they are very similar to eigenstate of what you call momentum or eigenstate in case of a free particle. We shall see that one, not normalizable, but it will help us to understand. Okay, these are eigenstates. Energy eigenstate, or you can write as definite energy states. These are individually definite energy state, isn't it? No uncertainty in the measurement of energy in these individual state, but there will be uncertainty in here. Okay, now look at here. If you do the measurement, what you got? You got either psi1 or psi2, isn't it? Exactly in the same manner, if you do energy measurement, either you will get E1 or you will get E2 or you will get E3. Here there is no possibility that when you do the measurement, electron will split into two and it will pass through both slit. Like you feel here, isn't it? In case of superposition state, it will not happen. It will show off either one translation state or other translation state. Exactly in the similar manner, if you do the energy measurement, it will show any one of the energy eigenvalue, and state will be collapsed to that particular eigenfunction. Is that okay? So that is the idea. So now later, look at here. Then we defined one more thing. If you try to normalize this one, x comma t gs psi x comma t gs dx over all possible space, that's equal to 1. This is equivalent to, actually I have shown, summation over mod cn square n is equal to 1 to infinity is equal to 1. Okay, these are equivalent again, so you will understand that. And one more thing is, you can't say which energy it is. It can be either, again, if you do the energy measurement, you can't say which energy it is, either E1 or E2 or E3 or something, isn't it? Now you can talk about probability of energy measurement, am I right? Probability of getting En, that's equal to mod Cn square, provided total probability equal to 1. Is that okay? So provided, we should make sure of this condition, n is equal to 1 to infinity mod Cn square is equal to 1. That means total probability equal to 1. Okay, once you get this one, once you get this probability definition, so is that clear? Any question here? So can you compare these two? That is also superposition state, superposition of translation state. This is superposition of energy eigenstate or superposition of different definite energy states. Is that okay? So when you do the observation, it will show one of the translation state. When you do the observation, it will show off one of the eigenstate, energy eigenstate. That means when you do the energy measurement, you will get one of the eigenvalue. These things will become theorem later. Yeah.
But in translation state, we are saying the amplitude.
A wave amplitude. That's true, but
here we are applying Cn.
That also plays similar role actually. Later we shall see some. What you call, how to club all of these interpretation into one domain. Here this is a coefficient. Am I right? So here also, suppose here if you put 1, if you put 2 here, then amplitude will differ, isn't it?
Yeah.
If you put 1 and 1, it's a kind of, it is equally probable. Next electron, whether it pass through slit 1 or slit 2, that's equally probable, isn't it? This again, suppose if you take what you call so inside that psi 1, if you make amplitude same, then you are putting same coefficient here, isn't it? While adding that coefficient, will also talk about probability actually. Is that okay? Here also, but that is to understand. Okay, this experiment is to understand the superposition state and measurement outcome. Is that okay? Because that kind of state mathematically is not normalizable, translation state. We shall see that one. Is that okay? Speak out. Now, so this is exactly same. Again, what you have to grab the idea, once it is a superposition of different translation state, your measurement outcome is that individual translation state, not something superposition state. After measurement, you will not get any superposition state. It is one of the translation state that it composed of, isn't it? Similarly, so this is the superposition of different energy eigenstate. When you do the measurement, your outcome is one of the energy eigenvalue. Is that okay? Can you hear me? Speak out. Yeah. Now, once you define it like this, okay? Once you define this probability, this is a discrete probability distribution, probability of getting E1, probability of getting E2, not just like mod psi square, density kind of thing, isn't it? So now you can define your average energy. Average energy is nothing but expectation of Hamiltonian. That is equal to, in this state, okay? In this state, because in this state only I have defined probability. You will get n is equal to 1 to infinity. So En into probability of getting En. Isn't it? That's equal to summation over n is equal to 1 to infinity En into mod Cn square. Is that okay? This is a average of energy or expectation value of energy you can find in that particular state. In case of this linear combination state, let me call like that, okay? Yes, read out book, okay? So today only, so that you'll feel comfortable. Now you can find expectation h cap square. That's also equal to n is equal to 1 to infinity En square into mod Cn square. You should first make sure of this condition, okay? Clear? Now look at here, position probability interpretation is same. That means, so this is the state you are talking about, general state, okay? So this is position probability density. Is that okay? This dx is probability of finding the particle from x to x plus dx. This probability definition is not changing, okay? So again, you can do this interpretation once you have normalized. After normalization, you can go for this probabilistic interpretation. Speak up. So now that's why what I'm saying here is this part didn't change. Along with that one, this is a superposition of different energy states, isn't it? What is the probability of getting energy outcome? That is another probabilistic interpretation. So what I'm saying is, so this wave, we say this is the state, am I right? This is the wave function. So generalized state, am I right? X comma t, superposition state, whatever you say. N into Cn into psi n of x into e power minus I En t by h bar, okay? Now, since there is an uncertainty in the measurement of energy, so there comes what you call probability definition, isn't it? You don't know which energy you are going to get after measurement, but you can talk about probability. This is one of the probabilistic interpretation. You can call it as Born interpretation only. Later we shall prove again everything is almost similar. Is that okay? But what about probability of finding the position of the particle? Here I talked about probability of finding the energy, isn't it? Probability that energy outcome will give the value En. So now what is the probability of getting the position of the particle? That definition didn't change. Is that okay? That is this one only. Mod psi x comma t whole square dx. That's only probability of finding the particle from x to x plus dx. That didn't change, okay? If this is the wave function, this is the probability, this is the position probability interpretation. That didn't change. Make sure that total probability equal to 1. Okay? But you are doing the energy measurement. Remember, what measurement you are doing? That does matter, am I right? If you are doing position measurement, so this is the interpretation. This is position probability density multiplied with dx, probability of finding the particles from x to x plus dx. Probability of finding the position of the particle. That interpretation earlier, that remains same. But here, another measurement comes, am I right? Along with position measurement, energy measurement. If you do the energy measurement, what is the probability of getting the energy? That is this one. Clear? Later we shall show they are very similar, okay? They are very similar, what you call, kind of inner product like that. We shall see that one. So position probability answer, position probability is continuous, but energy probability is discrete. That's why you go for this kind of summation kind of thing, am I right? So suppose here, if you need expectation x in this state, in this generalized state, again the same idea. Same idea. But if you need any anything regarding energy, you should use this one. And that is summation, that is integration. So can you divide these things and note down? Okay, two different things. Two different probability definition came here. Okay, let me rub out this one. And you should imagine this one as similar to what we call double slit experiment, because when you do the measurement, either you will get E1 or you will get E2 or you will get E3 like that. You can only talk about probability. You can't say what is the energy going to be, what energy that you may get after the measurement. You can't say before the measurement. Uncertain. Now usually in the most general case, these two will be not equal. Okay, the square of this one and this one, these two will be not equal. You will get some sigma which is non-zero.
So sir, in linear combination state, we can measure position of probability.
Again, that take the total state, normalize and do. This total state is also one function, am I right?
So that will be very helpful for solving problems.
No. Again, it all depends actually. If they give linear combination state, most of the case they ask about energy something, average energy or something. Is that okay? It all depends on the situation. Don't decide it right now. Is that okay? That's what I'm saying. But again, what I'm saying is in the linear combination state, what is the probability of finding the position? Same argument, not any different. Okay, you should take the total function, you should normalize, and mod psi square gives the probability density. Is that clear? Yeah, you do the problem, then I think you will understand. Okay, so this is one aspect. I hope now this part is over. Okay, we can start with particle in a box in the second chapter. But in problems, I might have, look at here, I have shown psi of GS, okay, x comma t, that's equal to summation over n into Cn into, how to say, psi n of x comma t, or I have shown Cn into psi n of x into e power minus I en t by h bar, isn't it? One thing you should remember here, okay? You are again, you have shown that mod psi n square is equal to 1, dx is equal to 1. You say these are all normalized eigenstates, okay? Normalized. Whatever you substitute here, these are normalized, okay? After making linear combination, this need not be normalized, isn't it? You should enforce that condition. These are individually normalized. After making linear combination by multiplying some constant 1, 2, 3, 4 like that, the total state need not be normalized. You should enforce that condition, isn't it? Yeah, what you're thinking? Yeah. So now mod, again look at here, this is you are enforcing or like this. So psi n x comma t mod square dx is equal to 1. Okay, this is normalized. Okay, that's okay. But once you do the linear combination, it need not be normalized, isn't it? That you need to enforce that condition. To prove that one, whatever the expression I have written, you need one more property. These are normalized. Along with that, they hold one more property, psi n star into psi m dx is equal to delta mn. I'll not write delta m. I'll write in this one. That's equal to 0 if m not equal to n. Anyway, it is normalized. If m equal to n, this is mod psi square. It's equal to 1 if m is equal to n. They follow one more thing. I mean, if you have psi 1 star into psi 2 dx, okay, or psi 3 star into psi 1 dx, these are all 0 actually. Even you can take this energy factor also, that doesn't matter, okay. If you take time dependent factor, this factor, they will come out of the integral. These integrals are true, okay. Even if you take if you define the same thing with psi n of x comma t, same thing is true. Is that okay? We say they are orthogonal, okay. Word orthogonal, but this word is used in case of vector. I'll help you later how to think that these things are orthogonal, kind of vector dot product like that. Is that okay? Speak out. Are you okay? Is that okay? We call that one as orthogonality relation. Hold on, okay? Again, that word may be quite misleading for you right now. Later we shall see why we call this one as orthogonal, why that word which is similar to that of again which we use for vector, why that word came here. We shall see that one later. Is that okay? Now look at it. So that's why again this can be proved. So using this relation, if you just use this relation, so psi star gs x comma t into psi gs x comma t dx is equal to 1, am I right? Over all region. So this is equivalent to, you will see, this is equivalent to summation over n mod cn square is equal to 1. Using that relation. This relation is also required to prove this one. Okay. Anyway, that we shall do later. So what kind of normalization it is? Believing that mod psi square is probability density, isn't it? What kind of normalization it is? Believing that mod cn square is probability of finding the energy, isn't it?
Yes.
And total probability equal to 1. Both are similar. That's what I'm saying. Both are equivalent actually. Both are equivalent.
Sir?
Yes.
Sir, if psi n is normalized, then psi gs is normalized or not?
Psi n is normalized, then?
Psi g
No. Again, if psi n are normalized, these are normalized, okay? These are normalized, but this need not be normalized. You need to enforce this condition. You can put any coefficient, but you should take care that summation over mod cn square should be equal to 1. Is that okay? If you put arbitrary constant along with that one, that need not be normalized state. Is that okay? To normalize that one, you should go for this one or this one. Is that clear? You should enforce that condition.
Yes.
These are normalized. These are earlier. Again, we normalized and we started this one. Okay. These are normalized earlier individually. Okay. But once you do linear combination, it need not be normalized. You should enforce this condition or this condition, whatever. Both are equivalent. Okay. Yes. Speak out. Now, what I am saying here is, look at here, this psi star into psi that we write. Am I right? Integral psi 1 star into psi 2 dx. Am I right? We write like this. This is, in case of Dirac notation, it is written like this. Psi 1, psi 2. Dirac notation. So again, in the problem, there are many Dirac notation questions. Am I right? So they say state 1, state 2 like that. Take it as psi 1. Take it as psi 2 right now. Okay. Later, after working out Dirac notation, you will feel Dirac notation is easy. Okay. Again, look at here. You don't have to write integral at all. You can write some symbol here, isn't it? Some other symbol here, isn't it? That's why that's quite handy. But right now, since I haven't introduced Dirac notation in any problem MCQ that I given, if you find this kind of thing, take this one as psi 1, take this one as psi 2. Is okay. So there is one thing, psi at t, psi at 0. They are orthogonal. Am I right? He said wave function, find the time at which wave function is orthogonal to initial state. Am I right? That means initial state is psi at x comma 0. Okay. So that is the initial state. Or simply we write psi at 0. Psi at t equal to 0. Okay. So psi at t greater than 0. So now that is what is the orthogonality relation? Psi at t greater than 0 star psi at t equal to 0 dx is equal to 0. If they are orthogonal, this relation will be satisfied. If these two are orthogonal, okay, we call they are orthogonal. Psi 1 and psi 3 are orthogonal. So we call psi 1 and psi 2 are orthogonal. Okay. Don't think much. I'll explain why that word orthogonal came here. Okay. I'll explain that one. So similarly, there are questions. They have given initial state. At what time the final state is orthogonal to initial state? You should take orthogonality relation and equate that one to 0, and you should find the time. Is that okay? Psi at 0, so t equal to 0 actually, and psi at t, isn't it? They are orthogonal after some time. Find that time. Then put that one in an orthogonality relation and find the time. Is that okay? Right now. And if any of these things comes, take it as psi1, take it as psi2 and proceed with that one. Is that okay? Later, after working out Dirac algebra, I think you can do in Dirac notation itself. Okay? Any questions? Yeah, now shall I move on to differential equation? Yeah, any question? Quickly. Measurement, okay, that last class was very important. If you wish, watch that video again or beginning of this part, okay, or read book carefully, sentence by sentence, okay. Yes, tell.
The probability basically, I mean, we have two types. One,
now we have two types, one more type will come later. Probability of measurement of momentum, isn't it? That we haven't defined yet, isn't it? Yeah, like that. Yes, tell.
So in one we are measuring like cn square will be 1. Cn square will be 1. In another
some integral of mod psi n square is equal to 1. That means one is a continuous probability distribution, you need integration to normalize. Other one is discrete probability distribution, you do summation to normalize.
Okay.
Is that okay? That's simple.
So if one wave function is not normalized, like psi n is equal to a e to the power minus ax square, we have to find that a.
Mod psi square, that is the easiest way because you haven't defined what is the eigenstate, what is its linear combination and all, isn't it? Just normalize mod psi square integral, normalize. Don't think about linear combination in that case, earlier problem. Okay. Now onwards, again, if the linear combination state is given, sometimes that summation way is easy to normalize. You will do problem, then you will understand. Okay? Yes, tell me.
Sir?
Yes.
What is the difference between the average value of the measurement and most probable value of the measurement?
Now again, look at here. I told that one in the what you call in the mod psi square distribution itself. Am I right? Mod psi square. Your average x may be somewhere here. So, but this is where your probability density is maximum, isn't it? So similarly. So similarly, in case of what you call so probability of En is equal to mod Cn square. Okay. So when this mod Cn square is maximum, that is the most probable energy, isn't it? So you will have set of this value among them when that mod Cn square is maximum. So that is the most probable energy.
Okay.
Is that okay? Average energy need not be any of this En. Okay, average energy is again you have to take this one En mod Cn square. This is average energy. Is that okay? Remember that average energy or expectation value need not be any of the possible outcome. Can you hear me?
Yes, sir. Yes, sir. Okay.
Average value need not be any possible outcome. Suppose if you have only two states, okay, average value may be between E1 and E2. Suppose you have two states of again one state corresponds to energy E1, other state corresponds to energy E2. You linearly combine them. Your average energy will be between E1 and E2. But what is the measurement outcome? That is either E1 or E2. Measurement outcome is different, average value is different. Can you hear me? Speak on.
Yes, sir.
Yeah. Measurement outcome is different, average value is different. Is that okay? So that you need to observe here, okay? So because there are questions in JEST exam that they have asked what is the possible outcome? They have given on linear combination. Said what is the possible outcome? One of the answer is average value. Is that okay? Possible outcome is not average value. Average value is not possible outcome. Possible outcome is one of the eigenvalues. Speak out.
Sir, so
Yes.
To find most probable x value, we have to differentiate
Huh.
mod psi square.
You can differentiate mod psi square, you can equate to 0, you can find the maximum.
Okay.
You can locate the maximum. That's correct. Yeah. Now again, do problems, okay, more and more MCQs. Again, I'll upload some more MCQs today.